Not the world's biggest stats idea, but something you need to be aware of. Excuse me. They utilize a number line, just an X. Much like a frequency table. And we did a frequency table on day one when we did that activity with the beads and picking of the pilots. So let me just give you a scenario here for a dot plot. Let's say I take and I ask everybody their age. Okay? I think it's a fair bet that everybody's going to fit between 15 and 20. Age in years. Now, I bet I don't have any 15-year-olds. I have had them, but I bet I don't have any in here. I might have some 16-year-olds, but I bet they're on the older end of things. So maybe a couple of you are 16-year-olds. But I'm guessing, without doing a survey, that most of you are 17. And maybe there's one or two 18-year-olds. Maybe. I'm guessing probably not. Okay? But maybe there is. And I would also bet that there's probably not a 19-year-old. But that's a possibility as well. You're 19?
No.
Oh, okay. All right. I know there's no 21-year-olds because they kick you out of school before you get to be 21, because then the teachers could have you go buy beer for us at lunch, right? They don't want the teachers drinking beer at lunch, okay? That's why the 21-year-olds don't get to stay in high school. All right. That's the only reason I can think of. All right, so what do? We draw and label. Draw and label the x-axis. Scaling it is important. You can't go from 11 to 15 to 16 to 22, and you just can't do that. Scale it correctly, and then we just plot the values. It's simple. I want you to know about it. You probably aren't going to be asked to do it much. You'll maybe have a problem or two today, and that'll probably be about it. And it works pretty nicely when you have a small data set. Now, what sort of shape did I draw? If I were to kind of throw a blanket over that, what sort of shape would we get for this graph? Normal, a bell curve, right. And a pretty narrow one at that. Most of the data fits in a very small range. Okay, we're going to talk about some of those ideas today. How could I have maybe changed the scaling? Can anybody think of a way that I might have drawn that where maybe it would make it a little wider and less people would fit just straight up into the 17 category? Months would be one possibility.
Do like 16 and a half.
You could half years or maybe quarter years or something like that. Anybody born now, whatever, 2002 in January, February, March fits in one, and something like that. Yeah, right? You could do something along those lines. So there's different ways. You get to pick what to do with that. So you can manipulate the way the graph looks based on how you scale it. All right. So let's talk about shape. That's how it looks. there are a few basic shapes that I want you to definitely know about. Of course, a graph ideally could be any sort of crazy shape. But the main one, and the one that we would like to see most of the time, is normal, or bell. The normal curve is symmetrical. I'll do the best I can to make it symmetrical, but my symmetricals aren't always great. That was not too bad, I think. One side matches the other. Some of them are wider and lower, others are taller and narrow, but they all have one thing in common. They all have an area equal to 1 unit squared. The area in stats is always 1 unit squared. Doesn't matter what the shape looks like. Always that. Which is awesome because then we don't have to do like calculus, area under a curve kind of junk. Okay? So this is the one that we're always shooting for. And to be perfectly honest with you, normal is theoretical. There really is no such thing as a perfectly normal curve when dealing with data. There's always going to be something that's going to make it a little out of whack on one side versus the other. Unless you're manipulating the data in some sort of statistically illegal way. All right? So what we get is we go to kind of get these different sort of ranges of normal. If it's a good normal, we just call it normal. Or if it's maybe a little funky, we call it approximately normal. You don't have to write these down. You'll see and hear these plenty throughout the next year. And if you're like kind of stretching it a little bit, it's like, yeah, it kind of looks normal, but it's a bit of a stretch, then we might call that roughly normal or very roughly normal. Okay? So there are sort of different degrees of normal, if you will. It doesn't change the way we deal with it, it just sort of changes how we describe it. Then we have skew. Let's talk about right skew. Right skew is has a long tail to the right. It would look like kind of like this. And again, the area, 1 unit squared. Notice I'm not connecting the horizontal axis and the graphs. There's always room for that to add more data, or you don't know how, you don't know how far that's going to go. Left skew. So it's exactly like the right skew, except it's the other way around. It's got the long tail on the left side. And again, 1 unit squared is the area. There's 2 more that I want to hit on. Of course, like I said, many shapes can occur, but a couple more that are fairly common. The next one isn't all that common, but if you see a problem with it, I don't want you to get mixed up on it. It's called a uniform curve. And a uniform curve isn't uniform at all. Or, well, actually, it isn't a curve at all, I guess I should say. It is uniform. It looks like this. It's a block. And if you think about it in terms of a histogram, each of the bars would have exactly the same height. Bump that up a little bit. And again, area equals 1 unit squared. You might run across a problem that gives you a uniform base is 1, has a length of 1, so this height would be 1. Or it could be, you know, something like this. What's the height of the curve? 1/2. Right, yeah, exactly. So base times height always has to equal 1. Yeah, good. The only other one that I can think of that we really might need to kind of concern ourselves with at times, but not really all that often, is a bimodal curve, or bimodal, oops, not the letter I wanted. A bimodal curve could look like this, perhaps. And it's where there are two high points. It doesn't mean that both high points are the same height. It just means that there's very definitely two peaks to it. If there's only a little bit of a dip between them, you probably wouldn't call it bimodal. But if there's a very definite dip, yes. So there are two maximums, you might say two relative maximums. This maximum is relative to the data near it, and this maximum is relative to the data near it. So, two maximums. So far, so good? All right. Got a couple more ideas for you today, and then we will get on to some problems. One of them, I get the impression that you guys haven't seen before. Maybe you've heard of it, or maybe weren't sure how to make it work. It's called a stem plot, or a stem and leaf plot. Now, a stem plot and a dot plot, the calculator doesn't really do very well for it. In fact, the stem plot, it won't do at all. Let's put some data down, and we'll make a stem plot. So, I've got 8 and 9 and 11 and 13 and 11 and 10 and 12 and another 11 and 20 and 21. So when we take data and put it into a stem plot, we split the data into two different parts based on place value. So the place values that I have with these is I've got 10s and I've got 1s. Here the 8 has 0 10s and 8 1s, right? And the 9 has 0 10s, but here the 11 has 1 10 and 1 1. So when I make my stem and leaf, this is the stem, this is the leaf, I use the 10s. In this case, I'm going to use the 10s as my stem. So my smallest amount of 10s is 0, and my largest amount of 10s is 2. Because 21 is the largest number, and 8 is the smallest, right? So now I go through and I'm going to make the leaf will be the 1's values from preferably smallest to largest in each sort of section. So 8 is my smallest number. I'm going to mark it off. I'm going to put an 8 here. But I also have another number that has 0 10s. That's the 9. So that's going to go here. And now I'm going to go to my 10s. I'm going to look for the smallest one, that being 10. So I've got to put a 0 here. That represents 10. I have a bunch of 11s. I've got 3 of them. So I'm going to mark them off, and I'm going to put 3 1s. Okay. Next is a 12. So I'm going to put a 2 after the 1, representing the 12, and a 13. Now I've got a 20 and a 21. They go in as well, but they go into the 2. So there's a 2 and a 0 for 20, and a 2 and a 1 for 21. And there's my stem and leaf plot. Now, if all I gave you was this, and you didn't have the raw data, unless there's a key. So we need a key, and you can pick any number in there to choose from. I'm going to use the 21. So the key, you do something like this. You go 2, 1, and you can either write means or equals 21. And that sets the place value. So the thing about a stem and leaf plot, it doesn't work for large data sets, but it's pretty cool because the data is recoverable. You could take this with the key and rewrite the set of data. There's really no large data sets for this. It'd be a nightmare to deal with, say, even 100. 1,000 would be out of the question. There's one other cool thing about this. If you take the stem and leaf plot and turn it 90 degrees, you get a pretty decent histogram. And shape is visible and begins to become visible. So turn 90 degrees for shape. So what shape would you give that? What would you call that? Normal, I agree. I wouldn't call it approximately or roughly, I'd call it just normal. That's pretty close. Okay, I don't have any more graphy things. We need to talk about a couple terms now. Outliers. Outliers. Somebody in my first class gave me a really good definition for outlier. Before I define it, I'm just wondering, does that word mean anything to anybody? And if so, how would you define it? Yeah, something that stands out. Right. That's a good way of putting an outlier. Anybody else want to? Yeah. Well said. Yeah, a number that just doesn't quite fit.
Like something out of the normal.
Out of the normal. I like that. Yeah, all three of those are good things. If it doesn't fit, what do you mean it doesn't fit?
Like, set of numbers that are in a certain area.
Yeah.
There's one that's way out there. It just doesn't make sense to me probably.
It could be either too large or too small, couldn't it? Yeah. Yeah, Victoria.
I think about it like cows. Cows are herding animals, and when there's always one like all the way by itself, it's usually sick or pregnant.
I wondered where that was going, but okay, I like that. Cows, there's always the one that's
Yeah.
everybody's at the water hole, but one cow way over on the other side of the hill.
Yeah, it's sick or pregnant.
Okay, so here's how I'm going to define it roughly. It's data that's too large or small compared to the rest of the set. I like the cows. The thing the student said in class the other day that I really, really liked is this student said a very unlikely occurrence, which is kind of along the lines of where you were heading with that, all of you really, a very unlikely occurrence. We were kind of looking for that on day one when we did that activity with the pilots. Weren't we trying to see if the outcome that they got was a very unlikely occurrence? Yeah, we were looking to see if it was an outlier. Now, a true outlier might fall a little farther away than what we discussed that day, but here's the thing about outliers. don't regularly just outright call something an outlier. Here's why. Let's say I took a survey in this class and I asked everybody, how much money do you make in a year as high school seniors? And I'm going to guess that probably on the high end, maybe somebody makes as much as maybe $6,000 or something like that. Maybe on the lower end, you know, $1,000, $1,500 in a year, something along those lines, I'm guessing. Excuse me, depending on how much you work or where you work or, you know, if you work, those kinds of things. Now, throw me into the mix. My income would be an outlier in that set of data, would it not? I would hope so. Okay, I hope so. I do make a little bit more than $6,000 a year. Okay, so I would become an outlier in that condition. Now, what if I compared my income though to, say, the household incomes of your families? Would I become an outlier then? You think so? Probably not a high outlier. No, I think I'd probably be about maybe middle, maybe a little lower middle or something like that. We teachers do okay. We do all right. Okay. So we don't really say something's an outlier because even if we calculate it, and there is a way to do that, we'll learn how to do that shortly. Even if we calculate that something is an outlier, we still have to take context into the situation. In the context of high school seniors, my income would be an outlier. But in the context of general household incomes in the greater Boise area, I'm probably not an outlier. Darn it, I'd like to be a high outlier, okay, but I'm not. So we say suspected outliers. Because context comes into play. Sometimes something might be perfectly reasonable, and yet numerically we might find that it's an outlier. And here's what I have to say about teachers' salaries. Yeah, I'd love to make $10,000 more a year. I'd love it. But you know what? If I made $10,000 more a year, guess what? I'd still want another $10,000. Right? That's sort of how it goes. So you sort of figure out what works for you and you make it work. How I make it work, I pay for a house, but I don't pay for a car. Well, not much. The car that I've driven for the last few years is a 25-year-old Suburban. And when I bought it about 4 years ago, I paid less than $2,000 for it. Now, what's a new Suburban cost? Well, I can tell you, I've shopped them just for the fun of it. About 70 grand. Okay? What does the new Suburban do that the old Suburban doesn't? Bluetooth. That's about it. Okay, maybe it has a backup camera. Big deal, I got mirrors. Okay? For $68,000 in difference, I'm good. Okay? And let me tell you something about a $2,000 Suburban that's amazing. You can park it anywhere. You know, if you have the $70,000 car, if you're driving a Ferrari or something like that and you go to the grocery store, you don't pull it right up to the front where some kid can like bash into with the door, right? If I had a $70,000 Suburban, I'd park it as far out as I could. And if somebody parked next to me, I'd be like, I got some four-letter words for this jerk, right? Okay? But with a $2,000 Suburban, you park it anywhere you want. Some kid bashes you at the door, you just bash him back. It's awesome. It's awesome. I'm telling you, there are things in my life that I like to be nice. There are other things where it's like, gosh, there's freedom in driving a crappy car. There really is. Oh, and I don't insure it. Yeah, okay, don't let me scare you. I do have insurance. If I hit you, you're covered. But what are they going to do? What are they going to get? Oh yeah, we're going to give you $800 for your Suburban, sir. We know you bought it 4 years ago for $2,000. We figure it's worth $800 now. What do you mean? I've been giving you $800 extra a year to insure this thing. If I crash it, money, man. It's all about money. Make wise choices. That's my wise choice. I say drive a crappy car. Have something nice somewhere. Maybe it's something totally different. For me, it's a dirt bike. Okay, variability. Yeah, my dirt bike's worth more than my car. Okay? And it's quite a few years old too. How much variability deals with spread? Okay, how much range or spread is there? A data set has. I won't lie, I'm a little frustrated when I see you guys drive out with nicer cars than I've got. Okay, but I bet my dirt bike's nicer than most everybody's. All right, so variability has to do with how wide or narrow the data fits into. Low variability and right now I'm not driving the Suburban. My sister gave me her old Civic. She was probably feeling pretty bad for me. It's really nice. She's done a really nice job of keeping it up, but it's almost got 250,000 miles. And I love it. It's awesome. Again, I don't have to worry too much about dings and scratches. And I don't insure it. I get the basic bare minimum insurance. Low variability is going to give a tall, narrow curve. Kind of like when I was talking about if we did a survey about your guys' age. There'd almost be no variability at all. I bet almost everybody's 17 or very near it. Okay? So somebody's going to come up after this and go, yeah, I'm a savant, I'm like 14. Okay, so low variability as a graph would look like this, perhaps. Really tall and narrow in relation to the data. Still, the area in there is 1. Okay? That hasn't changed. But if it's not very wide, it's got to be tall for that area to work out. Let me introduce this idea with a little bit different scenario. Anybody in here like to target shoot? Maybe hunters? Yeah? Okay. So maybe you shoot with a gun, or maybe you shoot with a bow and arrow, or maybe you shoot with spit wads. That's my favorite. Okay? But I don't really care what I'm shooting with. I enjoy it any way I do it. I'm not a hunter. But if you put a gun in my hand or a bow and arrow, I'm gonna pull the trigger. So let's say you're shooting at a target and you have low variability. Low variability doesn't necessarily mean that you're hitting the dead center of the target, but what it does mean is you're getting a good, what do you call it, a good grouping, right? So maybe you're not hitting dead center, but all your shots are in a pretty small area. That would be low variability in terms of a shooting range kind of situation, okay? High variability, make this fit on this page. High variability is going to be a wide, low graph. Oh, curve. Let's say curve instead of graph. Thanks, sir. I'll get you some notes in just a second, Dane. Okay, a wide, low curve. Again, area is still 1. And if I were to compare that to shooting range again, maybe with high variability, I might get some in the center, you know? I might get some really good shots, but I'm also getting some really bad shots too. The data's going all over the place. The bullets are sort of all over. So high variability, low variability. Let's see, Dane, did you get a calculator and a book? You might want to grab one of those. Okay.